I welcome you once again to another video series on Real Analysis 3. So, from our previous explanation, I noticed that we actually pick an example 6 of this lecture, which says consider fnx, which is equals to nx all over 1 plus n squared x squared. And I believe, um, okay, and I was able to show the proof. I was able to show that it is pointwise convergence, which is equals to 0. And at the same time, I decided to explain the step-by-step explanation on how to test for the uniform convergence. And at the end of the day, we end up having a result that is being absorbed, even though we actually take, if we decide to take our epsilon to be 1 over 2, it is clearly seen that 1 over 2 is not less than 1 over 2, which is very, very absurd, which is not true. Then in that case, we can actually say, so in that case, since the result for the left hand side and the right hand side seems to be which actually seems to be absurd, then we can say that we cannot, which is not true. Then we can say that there is no natural number n such that the absolute of this fnx minus the f of x, which is pointwise convergence, is less than epsilon. So I think that will just be the final conclusion. So I would like to pick another example that is very similar to this, so you can get it clearly. And the next example is that let's assume that we are given a sequence function, and then we now want to consider whether there exists a natural number n that satisfy the definition of uniform convergence. So let's confirm. So let's try to confirm that. So the function I'm going to pick is a very, I think it's not too complex, but let me just go ahead and pick it up. So in this case now, we are actually given fn of x. Okay, that will be example 7, right? That will be example 7. Okay, example 7, which says given, okay, consider, let me put it this way, consider the function fnx is equals to n squared x 1 minus x then raised to the power of n. Okay, for this range, here is the range here. Sorry, please just hold on. Hello, sir. Hello, sir. Hello, sir. Yes, sir. All right. Am I just saying so? Okay, sir. Please. All right. So sorry for that. Concerning the question, okay, let's come back to this. We have considered the fnx, which is equals to n squared x, open bracket 1 minus x is to the power of n. So here is the question. So what we have to do now, we want to confirm whether there is no natural number n that satisfy the definition of uniform convergence. Then how are you going to go about this? First I will need to show that it is pointwise convergence, right? And then, so that means in this case now, I can actually have something of this nature whereby, okay, I was given fn of x, so I need to find f of x. And f of x is defined by this expression, which says if I take the limit as when n tends to infinity of fnx, it will actually be equals to f of x. So if this gives us 0, it is pointwise convergence in that case. So now looking at this expression here, so now let's take the limit of the sequence of function given to us. The sequence function given to us. The sequence function given to us is n squared x, and I have 1 minus x is the power of n. So what will this give us? Now looking at this expression now, I've already given you a particular clip that if you have something of this nature, okay, n tends to infinity, that means I will substitute n as infinity in any way I see it. And I gave you some clue in the last video that whenever you notice that you have a function and then it is being raised to the power of infinity, just know that everything here becomes 0. If it's being raised to the power of infinity, it becomes 0. So 0 times anything here, that becomes 0. So now since we have this, then we can easily say that therefore, okay, let me just put it this way. Therefore, this sequence function fnx, where n starts from 1 to infinity, okay, converges. Is it just converges? No, it converges pointwise, or I say it is pointwise convergent. Okay, so it converges pointwise to the limit. Okay, it's converges pointwise. It converges pointwise to the limit function. It actually converges to the limit function what f of x. Okay, to limit function f of x. So which is actually given by f of x equals to 0. So this is what it converges to, right? Now that's the first thing. So we have already shown that it is pointwise convergence. So that means if you are given the function and that is to show that it's pointwise convergence, you just try to find the just take the limit as when it tends to the infinity of that function. So you end up having 0, or I think anytime you have n tends to infinity, you can either have two answers. Most of the time you can either have two answers. It's either you have 0 or infinity. It's one of those two answers. So if you have 0, that means pointwise converges. But if you have infinity, that means it diverges, or you say it is not, or it does not converge pointwise. It is not pointwise convergent. So that's all you can say. Now let's test for the uniform convergence. Let's test for the definition of uniform convergence to confirm whether there exists a natural number small n that will satisfy this expression that will be less than epsilon. But in this case, I want to take my epsilon to be equals to half. Okay, so we use that to give our final conclusion. So that's how it works. Now, to test for convergence, right? To test for convergence now, the first one I did is for pointwise convergence. Okay, now sorry, to test for uniform convergence now, that's what I want to do. Now, to test for uniform convergence, how are you going to go about it? You know where we used to start from now. We always start from the derivative at turning point, right? So we always take the turning point. That will be the first thing you need to think. So to show that now, I will have to call that sequence function again. The sequence function is given to us as n. Let me check it again. N squared x. We have it as n squared x, open bracket, 1 minus x raised to the power of n. Now, I need you to pay full attention to this. Just calm down and listen attentively. For uniform convergence, write out the sequence function first. Then the second step, you are expected to differentiate it. So if you don't know how to differentiate, that's another problem entirely. Okay. Now this is you are different. You are looking for f prime of xn. You are actually differentiating with respect to what you have here in this bracket. That means you are differentiating with respect to x. If I want to differentiate this thing with respect to x now, that means any other letter I'm seeing is a constant. This is n not squared. Okay. So any other letter I'm seeing is a constant. Just like saying this is just like saying you're having something like 4 squared x, then 1 minus x is to the power of 3. You understand what I'm trying? Just assume it's just like a constant. So that means looking at this kind of expression, that means I'll call this one my u, then I'll call this one my v. Then it becomes product true since they are multiplying each other. Okay. So in this case now, I'll just advise you to take n squared separately and then consider the derivative of x and 1 minus x is power of n. Or anyhow you want to do it so that this one will be your u and while this one will be your what v. But n squared remain as a constant and I will not touch it. Or better still, you can call the whole of this one u and then you can call the whole of this your v since they are multiplying each other. I think let me just use it this way. So I'm very sure this is what you guys might be familiar with. But if you do it this way too, it's also correct. Okay. I would have loved to do it this way, but don't worry. Let me just go ahead with this since you can actually say this way. So since my u, I'll write it somewhere. My u is n squared x, right? And my v is 1 minus x raised to the power of n. So if I find my u prime, which is differentiates n squared x, n squared is a constant, right? So if I differentiate, it's just like say I'm differentiating 2x, that's 2. So if I differentiate n squared x, that would be 1 times n squared, that's n squared. X is power of 1 minus 1, that's 0. And x is power of 0 is 1. So if I differentiate this, I should have n squared left. What of v prime? To differentiate this expression here, this n will come down, write it. Okay, this n will come down, then times differentiate what you have inside the bracket. If I differentiate 1 minus x, I believe that should be minus 1. Okay, do you understand that? So since I have this result now, then I'll have to repeat everything back and then subtract 1 from here. I believe you're familiar with that from calculus. That is the idea of calculus. It's also the same thing as if you have ladder. Call Mr. Balala. Look at my phone. Look at number. Check the missed call. Sorry for that. I get credit time. So now looking at this now, I have n, I have minus one, I have one minus x is power of n minus one. I wanted to explain something of this nature before I got interrupted. So this one is raised to the power of five. Assuming you have something like this, this five will come down times. Let's say this one is x squared. You now differentiate one minus x squared. That's minus two x. You have to repeat everything back, and then you subtract one. Four minus five minus one. That's four. So that's what I've done here. So I believe that's not an issue. So if I look at this, this is just minus n, open bracket, 1 minus x, n minus 1. And this, since this is a product rule, I'll just write out, okay, if I want to differentiate now, I'll write out the formula for product rule. That's u v prime plus v u prime. And what is my u? U is n squared x. And then my v prime is what I have here as minus n, 1 minus x, n minus 1. Then I'll close the bracket. Then plus my v is already 1 minus x is to the power of n. This is v here. Then u prime is already n squared. N is to the power of 2. Why am I writing this n as 2? Okay, now if I expand this now, this is u v prime plus v u prime. So when I have this expression there, it is clearly seen that if I expand this, I should have minus n cube x, open bracket, 1 minus x raised to the power of n minus 1. Then this should be plus n squared, 1 minus x raised to the power of n. Do you know that after writing out this sequence function out, and then this second step I has to do is to take the derivative of that sequence function. Do you know that at turning point or at stationary point, we always have our derivative f prime n of x to be equal to 0. I think that was what I did in the previous video. Okay, so that means you have to set this result here, this f prime n of x, you have to set all this one to be equal to what? 0. And then you make x the subject of the formula. That is where the issue comes in. So if my derivative is already of this format, n cube x, 1 minus x, n minus 1, then plus n squared, 1 minus x raised to the power of n equals to 0. So looking at this expression, I can decide to bring this term to this other side such that I will end up having n squared. This one is already here, raised to the power of, this is n. Why am I writing n as 2 like this? This is n. So that will be equal to, then this comes like this. I have it as n raised to the power of 3. I have x, and I have 1 minus x raised to the power of n minus 1. So let's see what we can actually deduce from here. From this case, I should have make 1 minus x raised to the power of n as solid of the formula, but it does not really mean. So I can decide to divide both sides any how I want it by n squared, such that if this cancel this, I'm trying to make x the subject, and if this cancel this, I'll be left with n up there. Now I'm having 1 over x, I have n. Then here in this case, I have n left, and I also have x, and at the same time, I have 1 minus x raised to the power of n minus 1. Now, looking at this expression now, I still want to make x the subject. What if I decide to divide both sides by 1 minus x? Okay, divide this one by 1 minus x, and also divide this by 1 minus x, and check what is going to happen in that case. Now, looking at this clearly, you will get to see that if I divide both sides by 1 minus x n, this, and then 1 minus x is to the power of n, so this will automatically cancel this expression. I will just be left with 1 equals, okay, if this divide this, that means I should have an indices of this nature, n minus 1 divided by 1 minus x is to the power of n. Then that should be 1 minus x, right? I will subtract these powers. That's n minus 1 minus n. This will cancel this. So I'm only left with 1 minus x is to the power of minus 1. I hope that is clear. So that means if this divide this, I should be left with nx, then times 1 minus x raised to the power of minus 1. Okay, and then if I deduce this clearly now, that should be 1 is equals to nx times this one. Anything raised to the power minus 1 means this negative index, this negative minus, or sorry, this index or negative index, or yes, let me just call it negative index. This minus sign implies 1 over. Then I'll be left with 1 minus x raised to the power of 1. And if this one is 2 now, that will be minus means 1 over. I'll be left with 1 minus x raised to the power of 2. I'll put the 2 here. So when I have this expression, you know what to do. Just drop one and cross multiply. You see, it's already breaking down. It's making sense now than the way it was before. If I cross multiply, I will have 1 minus x here. And then in this case, I will have nx, right? So this is what I have in this case. So if I collect like terms, I should have 1 is equals to nx. Then this comes like this plus x. And I should have 1 is equals to x is common, n plus 1 left, right? So looking at this expression here, I will divide both sides by n plus 1 by n plus 1. So successfully, I was able to make x the subject of the formula. So my x now is equals to 1 over n plus 1. This x now is our x naught. Is our x naught in this case, is our x naught. So in our next video, I'll make sure I explain this clearly. Okay, I'll just continue from here.